And whenever you have simplify stuff, make sure you put your answers into a descending order. Reason why we use descending order is because it's more of a standardized style. And these, like I said, are pretty quick. You get 6x minus 3 minus 3x cubed minus 3 minus 6x. And then just combine your terms. Like I said, these are pretty quick. Start with the fourth. Go to your thirds. 6x is dropped, and you wind up with a minus 6. Okay. If you did not notice, yes, ma'am. No.
It's so hard for me. No. What's online? I posted it. If you look at,
If you are, I guess you're just wasting your own time. At this point in first hour, I was already probably like into factoring, so come on. I'm not fighting against you. If you don't want me to help you out, set the stuff up, it's fine. But if you go online, you'll notice that I did leave the answers posted through for you. I did not put them on that, so I saved a sheet of paper. So that's why it's not posted on yours, but it is on the internet, so you can check your work. Products, multiply, put in descending order. Long division. When you're working with long division, really the only thing you have to be concerned with is that you're putting placeholders in if you need them. If you don't have a placeholder in there and you're trying to do long division, you will screw something up. But remember, the name of the game with the long division was working with eliminating the first term. This one you don't have to worry about any of the placeholders. You have a cube, a squared, an x, and a constant. Okay? And you just play the role of how do you eliminate each successive term. What do you multiply x by to turn it into an x cubed? X squared, good. Which means you just place that above where you were going to put it, and then you distribute through. Subtract each part. I will strongly recommend to write the subtraction symbol twice, because when that second part happens to be a minus in there, you'll screw something up. So you get 8x squared, bring down the next part, 58x. Now you go, what do you multiply x by and turn it into an 8x squared? 8x. Bring that around. Subtract out. And now we have a negative value. We have negative 6x, I believe. Bring down to 41, negative 41, excuse me. And then you multiply it out now by a negative 6 and bring it around. And you have a remainder then of 1. Is that 1 positive or negative? You know, I was making sure you were paying attention. Congratulations. Great minds. Sir. Yes, sir. What do I put in front of it? A plus, good. Yeah. Yes, ma'am. Yep. And then a lot of times, I think more often than not, we get positive remainders because it's cleaner. But yeah, that's your long division. Just remember, you're just constantly eliminating each successive term as you're going through. A little bit easier than, I think this is easier than doing the division like long way with numbers. Because this way you know where you're going to get rid of. Okay. After that, we get into the factoring. And as you get into the factoring, you wind up with you kind of have all possible ways of factoring at your disposal now. What that means is that you could group, you could factor it like it was a trinomial, you could use synthetic division. You can do all those different things, and it's all up to you to what method you wish to choose. Some ways are easier than others. Some ways take longer than others, but they should still get you to the correct spot in the long run. For example, if I'm looking at number 9, if I'm looking at number 9, I see that I have 4 terms. It's going from cube squared singular to constant, which means always at that point, double check and see if you can group it. Okay? Because grouping, if it's possible, is quick. Or if I wanted to try and factor via my tails, I'd have to find all my factors of 4 and divide it by all my factors of 12. I'll get there, but it might take longer. So I group it to see if it's going to work right away, and you might recognize, oh yeah, sweet. I got a 3x squared, you got 4x plus 1. I got the 4, you got a 4x plus 1. Okay? That leaves you the 2 parts that are within parentheses are the same, which is good. Just like we did before, and what are you left with? 3x squared. Plus 4. Now, this problem said, hey, factor it. I'm done. I can't factor it any further than that. There's nothing left for me to do. All right? If this problem said solve for zeros, it would have looked like this. Okay? Now, just for argument's sake, what would you do to find your zeros for those 2 terms? All zeros. What would you do? Yeah, you set them equal to 0. So for this one, you get negative 1/4. And this one, you're going to get x squared is going to equal negative 4 over 3. And then you would have to do what? Square root it. What's the square root of negative 4? 2i. So I know I'm going to have x would equal plus or minus 2i over the square root of 3. But do you like the root 3's in the denominator? No. And you've done that a ton of times when you're in geometry and all that before. We've done a few of them as well. That just means you're going to wind up with plus or minus 2i root 3 over 3. So if it did say an equals 0, or it said find all the zeros, then you would have to take that extra step. But since it said just factor, you can stop. Okay? That's the idea, that just the very simple terminology of is it the zeros you're looking for, or is it terms? Okay? In this case, it's just terms. Ben? Do you have $1? Good. Give it to Dirk to make her day better. I'm gonna walk through both. I was joking. Now, in number 11, one of the things you want to recognize right away is that since you only have 2 parts to the problem, and one of them is a cube, that means you probably have a sum or a difference of cubes. Okay? Which means you have to remember the pattern. Well, first of all, what's the first rule of factoring? What do these guys have in common? 2. If I take out a 2, I'm left with 64x cubed plus 27. Well, it's a good thing because 64 is 4x quantity cubed, and this is a 3 cubed. Yeah. And that's what happens a lot of time with cube root ones. They hide a GCF in them. And the next problem is the exact same thing. The next one, if you haven't done it yet, I'm going to do the next problem as a subtraction one so you can see the difference between the two. But you have to remember how the pattern works. The pattern for difference is, sums or differences of cubes. In this case, you have the sum. It's going to be a plus b, a squared minus ab plus b squared. And what people will screw up, and Nina can attest to this, is that secondary part. Because our value of a happens to be 4x. When you square that, you don't get 4x squared, you get 16x squared. Also, since you're just factoring this problem, you can't just disregard the 2. The 2 has to come along for the ride because it's saying factor. 2 is a factor, it's got to continue with it. So this becomes 2 times the quantity, 4x plus 3, 16x squared minus 12x plus 9. And that would be your final answer. Okay. Is the other one 250 x cubed and a 1? 2? Are you guys okay if I just change that one instead of being a +2 to a -2, just to walk you through a difference of 1? No, I'm going to do it anyway. Again, what's your first rule of factoring? GCF, in this case, it's going to be, again, a 2. I have 125 x cubed minus 1. That is a 5x and a 1. Patterns for, when you have patterns for this one, when you're dealing with, yes, ma'am. When you're dealing with the patterns for the negative, a minus b, a squared plus ab plus b squared. So again, the mistake that you'll make will be squaring the 5x. And there you go. Okay. I'm not even remotely close to that yet. I'm working my way there. Yeah. I'm building up to all those. When you get up to here, when you start seeing 3 terms, when it's asking you to factor, when you start seeing 3 terms, you want to go ahead and start treating it like you would a trinomial, like a regular old x squared quadratic. What times what's 18? Oh, first of all, the first rule of GCF, or first rule of factoring. I'll get it straight one of these days. First rule of factoring, in this case, it is 3. So remember, you're factoring here, so you have to bring the 3 along no matter what. So x to the 4th, 5x squared, and a 6. So now you ask, what times 1 is 6? Then you add together to get 5. 2 and 3. Now it becomes x squared plus 2, x squared plus 3. And now that's fully factored. There's nothing left for you to do. Nothing else you can do. All right? Solve it. You may answer. No, but thanks. Correct. If this happened to have an equals 0 to it, what would your zeros be? Exactly. And remember, that's what you can get from that spot. All right? That is a fully factored answer. If it happened to have an equal 0, you would just take it the final step and do that. I just throw those in there from time to time just so you guys remember how everything works. Okay? That's what we're trying to, bum rush through all this. Ooh. When you start getting to the factor of factor everything, the rules that I was just showing you a second ago about, I can try to find all of my zeros, in this case, via synthetic division. Or since I have 4 terms going in a descending order, I can try to group them. There are many different methods to solve for your zeros. In this case, whenever I see 4 terms, and right away I recognize that I'm going to have a GCF here, or I can be able to factor them via grouping, I'm going to do that each and every time. Reason is because it's quicker. All right? If I group these, I have an x to the 4th, x squared plus 5. Take out the minus 4, I have an x squared plus 5, 0. So far, so good? That means the terms that I'm working with right now will be x squared plus 5 and then x to the 4th minus 4. I can't jump to my zeros yet because that x to the 4th minus 4 is a difference of squares. What's the square root of x to the 4th? What's the square root of 4? Is that a subtraction sign? Yeah. So you can break that in further. So it's x squared plus 5, x squared minus 2, x squared plus 2 is 0. From that statement, now I can go ahead and list out all of my possible zeros. I will have 2 real and 4 imaginary. I'll have plus or minus I root 5, plus or minus root 2, and plus or minus I root 2. And those will be my 6 possible zeros. If it's an equal 0, yes. Anytime you see equal 0, you got to list them out. Because that's what that means. Find the zeros. I forgot to change that header. But anytime, remember, I've always said, whenever you see an equal, you always go for your zeros. Anytime you see an equal sign, that means you got to find the zeros. Right. The next two are a little bit weird. Again, you're going to treat them very similarly to what you would a regular old trinomial. Remember, even though you're starting with I think it's an 8th degree. Even though you're starting with an 8th degree polynomial, you just continue to break it down. See how it goes to 4 to nothing? Well, that means that what times what's 16? You got to go to get negative 17. Yeah, negative 16, negative 1. So you have x to the 4th minus 16, x to the 4th minus 1. And aren't those both differences of squares? Yeah. So you get x squared minus 4, x squared plus 4, x squared minus 1, x squared plus 1. Hey, aren't some of those differences of squares? They are, but do I need to list those out if I'm solving for zeros? No. At this point here, I can go ahead and write down all of my zeros because I can. Even though I could break it down further and say x plus 2, x minus 2, x plus 1, x minus 1, x squared plus 4, x squared plus 1. I can do all that if I want, but since I'm doing just finding my zeros, why not stop? Wait. I know, but I forgot to change the header. All I'm saying is that whenever you, and I was just telling these guys, whenever you see an equal 0, find zeros. Okay? So this would be plus or minus 2, plus or minus 2i, plus or minus 1, and plus or minus I. Where? No, it's not going to be I root 2 because if I just subtract the 4, what's the square root of 4? Right. 18 is exactly the same. What I wanted to do is jump into ones we haven't done in a while. Write the polynomial. It's basically write the polynomial out that you would get if those are the zeros.
Yeah.
And what that means is this one defaults weirdly. If there's a 3 plus 3i, what's the other one? And then you multiply it out.
Okay.
We just did it without saying that.
Okay.
This was like a hint to remind you to do that. No. So in this case here, I would say let's just say hypothetically there's a question like that similarly tomorrow. The instructions would be write the polynomial of least degree with leading term coefficient equal to 1 that has the following zeros. And then you would know, oh, there's a 3 plus 3i, there has to be a 3 minus 3i because imaginaries always come in conjugate pairs. So with that being said, if I go through this, remember, that means I have a 3 minus 3i, and I have a negative 2 minus 9 as well. Yes, sir? You can, but it doesn't really get you that much further away. Because if you go through it the way that we've been doing it, remember that this is going to be, it's x minus the 0. X minus the 0. X minus the 0. And x minus 0. We wrote it out long form like that a bunch of times, and then realized that when you're distributing stuff through, you wind up with differences of squares every time. Remember, if I distribute out the negative to the zeros throughout this, I'm going to have x minus 3 minus 3i. X minus 3 plus 3i. Now, if you took out your 3's, you'd have a 3 up front here, and you'd have a 1 and a 1. It would be fine, but it's still going to get you through the same thing. Are these two things the same? Remember how we were doing this before? And I think I kind of have it written a little bit in the chicken scratch in the back there. If you treat this like this is an A minus a B, this is an A plus a B, that is in and of itself a difference of squares. First term squared, subtract the second term squared. And that's how this works every time. Whenever you see the conjugate ones like that, it's kind of a shortcut. So you know then that you're going to have the quantity x minus 3 squared minus 3i squared. That's what all that's going to FOIL out to be. Okay. So if you FOIL out, not kill a puppy, you get x squared minus 6x plus 9. Three squared is what? I squared is -1. So you get x squared minus 6x plus 9 minus a -9, which means it becomes. So all this junk on the left is that. Which means that when you do all the junk on the right, we have x plus 2 you have just that to worry about because it follows the exact same pattern. So you get x squared plus 4x plus 4 plus 1. And then you just have to distribute out two trinomials. These take a little bit longer. I probably wouldn't give you anything with more than one conjugate because it just gets really messy really quick, as you can tell. They're a little bit time consuming. I totally get it, and it's an easy process as you start going through it because it never changes. Yeah, and that's the one downfall. It just takes a little bit. Did I write fourth? I'm sorry. This supposed to be x squared. I just realized I did that. I was thinking what it was going to be when we multiplied it all out. Sorry about that. Yes, ma'am. They gave you just what are the missing zeros. I'm going to have you write everything out. Yeah, that's one of the downfalls when you use other software to create problems and try to get as many of them as you can. It doesn't do exactly what you want it to do, so kind of playing around. What's up, Blair? Nothing. What are you doing? Oh, I can jump by him. What? Get all these bozos. Hey. They are all tall, yeah. Hey, Shimky's all in the back. You know Shimky? No, you remember Shimky, right? Yeah. Hey, buddy. Later. Also, the car has Boyer. He's a nut job. Didn't you guys have him as a teacher? Or was he already? He might have actually. You know what? Yeah, he was probably already an assistant when you guys went through that. Oh, he was. Okay. That's funny. Gotcha. When you get to the ones, and this is kind of where I'm getting towards where you're at, and you're down with the plot the zeros. You'd factor everything the best you can, plot your zeros to your end behavior. With those, I'm only going to give you ones. I think some of those have imaginary. I'm only going to give you ones that do that with all real zeros. So don't worry if you have imaginary on that. Again, I can't select. Just crapshoot. So when it gets to the point where you start looking at where you want to find all possible zeros. And what I'm going to do with this one, I'm going to take it a step further. I'm going to find all my zeros, and I'm going to plot it via my end behavior. And I think I get real zeros with this one. I think I do. What's your first rule of factoring? DCF, what does this one all have in common? X squared. So I take out the x squared. Then I have an x to the third plus 5 plus 3x, or 5x, and then a 15. So in this case here, I can group it again. I don't have to do synthetic. So I get x squared. Hey, Devin, I'll email you a test. Good luck. So you get an x squared. From there, what are all of your zeros? Multiplicity at 0. Very good. You have multiplicity at 0. You have 0 twice. This would be plus or minus I root 3. This is at negative 5. Now, in this case, you couldn't graph this one because there's an imaginary root. Everybody okay with that? Okay. Now, what if, just for argument's sake for this problem, I wanted to make sure I showed you an example of how to graph something with multiplicity. Let's just say this wanted to be a negative, and this was just a plus or minus root 3, just for our purposes. Is that okay? Now, if I do this and I want to graph it, if I want to graph this, I plot, well, I have a 0, negative root 3, positive root 3, and negative 5. All I would have to do is label those parts. My dance moves tell me that I'm going to be down up. Are you okay with that? So all I got to do is remember that I'm going up through one, down through the other. I come up, change direction, and go back up through. It would look something like that because the multiplicity at 0. You okay with that? And that's what when you're graphing it, you plot your zeros, do your end dancing of where you're going, and just meander about. And if you have to touch a spot more than once, it means you just change direction at that spot and then come back up. No, you go through. The only time you change spots is if it's a multiplicity of 2. And I'm not going to give you anything else that doesn't have I'm not going to give you a multiplicity of 3. Like I told you that. I think I said that yesterday. I'm only worried about multiplicity. Yeah, it just goes right through. I'm just giving you multiplicities. If I do, I would give you multiplicity of 2. They're going to ask me. You have 6. Just like
Okay, I
press
was
the
curious
buttons.
if they're supposed to do
You might not be able to, because they might all be imaginary. You'd have to use a calculator.
that. Okay. Can
Yeah, I see what you're saying.
okay, so it would just be the, which direction is it?
Yeah.
I think the last two is okay.
Yeah, and that's kind of what happens when you start putting these things together quick. We try to get us more problems without, because we did like every one of them in the book.
Yeah.
And then CUDA's great. They've got some great problems you can generate out of there, but you don't have the time to like literally go through every one of them. In this case here, there's the only thing you would be able to do, because they're all imaginary roots, the only thing you would be able to do would be say, oh, it's just down, up. That's all you would be able to do. All right? The problems that I'm going to have you graph, sketch stuff, you would have to know that you'd have real roots. Yeah, that's what I've been doing. Yeah, exactly. Just like I did, you know how I said, hey, let's make believe that this one was that root 3. I just labeled them out. Just label. Space it doesn't have to be perfect. You're just doing, it's just a generic sketch. Okay? So I'll ask you guys to graph stuff that has real zeros, dances, and things like that. What? No, you won't use that calculator. You don't need it. No, you wouldn't need it for it to solve it. Yeah, no, you wouldn't need it to solve it. Yeah, I'll have calculators for you guys, so won't worry about it. If you want. I just got to check it. Yeah, I remember that, because I know you kept that in your running doc thing. Come on!